All right, like I said, pre-preemptive apology for last homework. You need what I'm about ready to talk to finish part of it. But we're going to talk about page replacement algorithms. We want the lowest page fault rate. Why is that?
Page faults suck.
Yes. How bad?
Really bad.
Really, 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 really bad. So we can actually deal with the little performance problems with trying to select the correct victim, because that'll be totally eclipsed by the performance or what we'll save in runtime because of how bad page faults are. All right, so evaluate algorithm by running on a particular string of memory addresses. For example, these are the different pages that were being referenced, and how can we figure out page faults? All right. Graph of page faults versus the number of frames. Okay, obviously if you don't have many frames in memory, you're going to get a lot of page faults because you're not dividing it out. No one should be surprised by this graph. Are you surprised, Matt?
A little bit.
A little bit? Would you think it'd be a little more linear?
So create more frames.
Right, divide your memory out more, right. All right, FIFO, first in, first out.
Horrible.
Horrible algorithm? Yes, but isn't there a nice data structure for this?
I did the homework for this. It did not turn out well.
No, it did not, did it? It ended poorly. It did. All right, so 3 frames. Hey, look. 1, 2, 3. 4 has got to put that one because he was the first one in. Then 1 again because we just, whatever. Then 2. Oh, no, we got to do it again, do it again, do it again. So now we have 9 page faults. No, that's not good. So what came after 2? Came 5, and then 1, which was in memory, so that one's okay. Sorry, I'm up here. This one's okay because we'd have 5, 1, 2 in memory. 2 is okay because we still have the 2. 3 is bad, so we're going to replace him. 4 is bad, okay, and then 5, you're still in memory. Okay, good. What's weird about first in, first out is that if you add more frames, sometimes it's worse. So 1, 2, 3, 4. Then we need to bring in 5. Oh, wait, so 1, 2, 3, 4. 1 and 2, we're still good. 5 replaces 1. Okay, 1's back, so we got to replace 1. 2's here. Okay, we got to replace it because we just evicted 2. Now we're going to get 3. Oh, we just evicted 3. 4. Oh, we just evicted 4, so we got to put that in. Oh, 5. We just evicted 5, and we're done. So this algorithm is actually not just terrible. It gets worse as you increase the frame size sometimes. So this algorithm is actually really not optimal at all. This is an anomaly. This is not intuitive why increasing the frames actually produces more page faults. It doesn't make much sense. But the reason for it is, if you notice at the end it goes 1, 2, 3, 4, 5, and this kind of captures that, while the first one was able to at least jumble itself around a bit to try and capture a couple more hits, is what it comes down to for this example. Okay, we're going to look at it a different way just to make sure we're hitting home.
The homework.
Huh?
This one's like the homework.
It is. 7, first one, 0, second one, 1, third one. 2, not in here, so we're going to replace the first one because that was the first one in. 0's in there, so we're good. 3, not in there, so we're going to place a 0 because that was the first one in, first out. 0's not in, 3, 0's not in there, so we replace the 1 because that was the last one. 4's not in there, put the 4 in. 2's not in there, put the 2 in. 3's not in there, put the 3 in. 0's not in there, put that guy back in. Ooh, 3, you're in there. 2, you're in there. Good. 1 not in there, we'll put it here. 2's not in there, we replace the last guy again. 0's in there, 1's in there. And then 7's not in there, put him there. 0's not in there, put him right there. And then 1's at the end. All right. Everyone good? This is on your homework. You'll have a time to practice again. It may be on a midterm as well. So illustration of this anomaly. Basically, overall, yes, the number of frames do decrease, but you're going to have these ups sometimes of increasing the number of frames actually increases the number of page faults. So the optimal algorithm used for longest period of time. Now, optimal will just know that in the future, what you should replace. Is the optimal algorithm actually implementable? Why not?
Because you have to do code analysis.
You don't want to do code analysis. Okay. Right. You can't do code analysis. Sure. That's a good reason. You can't code analysis is not practical, and therefore knowing what the future memory references are going to be is not practical, so you don't know what's coming up. So when you don't know what's coming up, you have to use a heuristic. But the point is, you want to look at your optimal algorithm because you want to see how close your heuristic is to the optimal algorithm. It's a good way to gauge it, because if you're near optimal, then your algorithm's probably pretty good. Okay, optimal. So again, you load it in, there's not much you can do. They load the 2 in because they see that the 0 is going to be used many times and that 7 is not going to be used for a very long time. 0, used right afterwards. 3, they replace the 1 because they notice that there's a couple more, basically there's more than 3 different references before that 1 comes in. That 2 is going to be used fairly soon, as well as that 0 is coming up. So notice that the way it figures out what to replace is it looks down the line, what's going to happen next, and which one's the best one to replace. So you really have to just sit down and investigate it.
Your crystal ball.
Crystal ball. We call those oracles.
Well, that's the person that uses the crystal ball.
Right. He's the oracle. But someone has to know how to use the ball. You can't
You
just...
still need a ball too.
Sure.
You put the oracle and the ball.
And an oracle and a ball? Alright. Least recently used, the LRU algorithm. Hey, look, it's back. When did we see this before?
Paging last year.
Paging last year? Oh, sure. But more... Wait, did I really do paging last year?
Wait, was it paging or was it?
I think I did paging.
Yeah, you did. Yeah.
Well, okay, what was the other time we used LRU? Matt, you should be fresh.
Eraser.
We used it on erasers.
No, I just remember the LRU one because it was just like, bam.
And what structure were we using when we did LRU?
Something with the
Using-
registers.
Registers, yeah.
Structure though, like actual structure.
Yeah, what do we call it?
Like a stacky queue thingy?
Stacky queue thingy.
Like one of those things? Or?
You could think of it as a stacker queue. I know it's annoying where I don't tell you the answer, but this actually helps you remember. If someone can pull it out. So if I went over paging, ignore that.
Cache.
There we go. Yeah, so LRU is used in caches, which is kind of what this
Paging.
table is. Yeah. Anyways, I'm just trying to show you.
That's why I got confused.
Yeah, caching is the main idea, and then it's used everywhere. Everywhere. In fact, if there's a performance problem, that's usually the first solution.
What did you cache it?
Yeah, let's just cache it. Do hammer everything as a nail. All right. So least recently used, 1, 2, 3, 4. All right, that goes all in. 4. All right, well, I was used. 1. Okay, I was used. 2. Good. And then 5. When 5 is used, why are we replacing 3?
Because it was the least recently used.
Correct, because if you notice after 3, 4, 1, and 2 are used, so we can't do those guys. We need to go back to 3.
So basically count backwards on your reference string.
Or keep a
till you
counter.
find the
Okay,
fourth-
sure,
till
yeah.
you find the number of frames back
Sure.
number.
Sounds good, possibly. 5, 1, 2, and then 3. Why is, when you come 3 and 4 is evicted?
Because 2, 1, and 5 are the last 3.
And then 4.
2, 1 again, so 4 is the fourth one.
You got it. It turns out 4, we should have evicted that guy. Oh well. Put the 4 in. Why is 5 evicted at this moment?
Just whatever it is.
Because 1, 2, and 3? Good. And then 5, why is 1 being evicted? I was waiting for you to say we just went over this.
I was about to, but I thought you were telling me to hold on, let somebody else answer.
Oh, no.
Online people?
Chris, take it away.
Just took over.
Uh-huh.
4, 3, 2, 1's the fourth number back.
All right. Can we implement this one?
Yeah.
Yes, we can. Yes. Anyways. Every page entry has a counter.
We can implement optimal too.
How?
We get an oracle and a crystal ball.
Do those exist? Crystal balls, yes.
We do code analysis to take out the metaphor. We can do that.
Ah, no. That you are absolutely wrong.
I'm absolutely wrong. Why can't we do code analysis?
Halting problem.
Huh?
Halting problem.
It's the whole thing problem.
Wow, this is a great segue. All right. Let's say you have a program. You wrote a program P because we're doing code analysis. You have P and you have inputs. Because you're an operating system, you have the program and you have the inputs that are being fed to that program, correct?
Okay.
Can you write a separate program, we'll say B, that tells me that given a program and its input, does it halt?
Does it halt?
Does it stop? That's all. Does the program go into an infinite loop or does it complete? That's it.
Without running the program.
Without running the program. Well, you can run the program, but the problem is our program has to tell you whether it halts or not, so it has to generate. So if you run the program and goes in an infinite loop, your program's not going to complete. So that's not a legitimate solution. A legitimate solution will tell you yes or no.
Math.
It is math.
I feel like it could be done.
So in 1934, Turing proved that it is impossible. That program cannot exist. So
if I want to become a millionaire, I can write that program.
if you want to break the laws of math and logic, write that program. Because he proved beyond the shadow of a doubt.
A program will halt.
That what?
That will determine if a program will halt.
Right.
Basically if it will ever return.
Now, yeah, this is using a Turing machine, of course, which our machines are weaker than a Turing machine. So if you can do it on our machines, that'll be great. But if we can't determine if a program halts or not, doing full code analysis is not going to happen. Good segue.
Do we have to do full code analysis? Could we just look at the next 10?
Yes, but the next 10 lines of code is a four-state Turing machine. Then yeah, that doesn't work. They were able to show that if you have 2 or 3 states in your machine, your program, aka your program is incredibly simple, then you can find out if it's going to halt or not. But once it develops any level of complexity, it just can't happen. Of course, what I was telling you is, for general purpose, giving any program an input. So YouTube actually has a great explanation of this. I love it, and I'll show you that link afterwards. But back to this, so we cannot do full code analysis, but we can do LRU because we do know what happened in the past. Every page, is counter implementation. Every page has a counter. Every time the page is referenced to the entry, copy the clock into the counter, so you're having a timestamp. When page needs to be changed, look at the counters to determine which one to change. What's the runtime complexity of this? Of updating the timestamp, O of 1. Of finding what to evict, O of it. Okay.
Or n is the number of frames.
Right, n's the number of frames. And page faults are so bad that, okay, maybe this isn't that bad of an idea. All right, let's do examples.
And frames are probably not that big.
Hopefully n's not that big. But it usually is fairly large, but that's okay. 701, all right, those weren't in there to begin with, so we have to do it. 2, why is 7 replaced?
Or least recently used, we already did this.
You know what we did, didn't we?
Frames, go back.
No, that was the optimal. Then we did it here,
Yeah, right
and now-
there, that's what we did.
and now we're good.
That's what I'm saying.
Okay,
No,
fine.
we just changed
So we
it.
have another example.
So we're gonna ask us why on each one again?
Do you want me to skip this, Chris?
No, you can go through it. ask us why each time.
All right. 0 is already in there. 3, 1's replaced because if you go back, the other guys were referenced. 1 was the last one, or the oldest. 0's in there. That's great. 4, 2 is being replaced because 0 and 3 have already been referenced. 2 is replacing 3 because 0 and 4 were already referenced. 3 is replacing 0 because 2 and 4 were already referenced. 0 is that last one. 0 is going to replace 4 because, again, 3 and 2 were referenced. 3, we're good. 2, we're good. 1, okay, we're replacing 0 because 2 and 3 were referenced. 2's in there, we're good. 0, all right, we're going to replace 3 because if you go back, that was the last one referenced of this list. 1, we're good. 7, okay, we're going to replace 2 because if you go backwards, 0 and 1's there, and then you get a 2, 0, 1 are good.
Much faster.
What property of caches are we trying to capitalize on with LRU?
Property of caches. The LRU bit.
LRU bit. Is this spatial or temporal locality?
Oh, temporal.
Why is it temporal?
Because it's the least recently.
Right, it's time.
Yeah.
Because we're basing it on time, not that the fact they're next to each other. So again, we're using a caching algorithm, which we learned in architecture. All right, another LRU algorithm that is actually faster is you have a stack implementation. Well, maybe faster. You keep a stack of the page numbers in a doubly linked form. So when a page is referenced, you move it to the top, and that requires 6 pointer changes. You don't have to search for a replacement because you know that that guy is at the end of the list. For example, let's see, we going along this reference stream right after the 2, it looks something like this. 7 is referenced, so 7 from down here is popped up to the top of the stack, and notice that everyone else is essentially shifted down except for what was below 7, which is already at the end. So that means if we wanted to evict something from here, we would evict the 4 because it's at the end of the stack. This eliminates the need to look through the entire counters, but adds a data structure where you have a linked list. Let me just answer a couple questions. How does it know to go from 7 to here? Well, obviously that's where it is in the stack, so it knows what, it's got to keep a pointer up here to which value we're going to. And then it needs to be doubly linked because it needs, from when we jump to the pointer, we need to be able to go back to link him down here and of course go forward to link him back up there. So it does need to be doubly linked. And they said 6 memory references, and that sounds about right. So hopefully 6 memory references is faster than scanning your entire page table, which is probably the case. But that still can be a little tricky. Another thing they like to do is LRU approximation algorithms. If you notice, both of those are still somewhat overhead intensive. If you think about operating systems, we want everything to be as super fast as possible. So we'll just have a reference bit with each page associated, initially 0, and when a bit or a page is used, you set it to 1. Replace the 1 which is 0 if 1 exists. If we do not know, we don't know the order, however, but this gives you an approximation of what was least recently used. We can do a second chance bit. So you need the reference bit. If it's to be replaced in clock order and the bit is 1, then set it to 0. So the idea here is if it has been referenced, set it to 0 and then move on and leave the page in memory. All right, let's see if they give you a nice picture. At least it's the same bit. Here we go. Let's say we're currently looking at this victim. The idea with this approximation algorithm is you're going to have a circular queue, which is really just an array. Once you get to the end, you pop back to the top. Let's say you're looking here where the next victim is that you were looking at because you can keep track of where you are in the array. This guy has a 1, so we're going to give him a second chance by setting it to 0. That guy's a 1, so we'll give him a second chance by getting it to 0. Oh look, we just got to another 0. We'll go ahead and evict him because he has a reference bit of 0. Okay. So what's the advantage of this algorithm over the previous two of least recently used and the stack implementation? So in the true LRU, you had to go through the entire array. Do you have to do that here? Not necessarily. It could degrade to that, But on average, you're not going to. Someone's going to have a 0 in there to evict. What was the problem? Oh, I didn't actually go over that. What's an implied problem with the stack implementation? Can anyone see that? Or actually, what's nice about the LRU and this guy? All right, the nice thing is you're only appending to the table a bit. What's the stack implementation doing? You have your table,
List of
and then you have a separate list in memory, right? And why would that be undesirable?
more memory.
More memory, and that stack may not be close to your table, which means it wouldn't be in your cache as well. So it might take a while to bring it in. While this, it's with your cache lines, so it's going to be spatial locality will take advantage of your bits. So this is an approximation, probably a little faster than LRU to find something, although it may not be the best might not be as good as LRU when it comes to page faults. Oh, keep in mind there's, whoa, just realized what that stood for is least recently used, least. Hold on. Keep a counter. The number of references that have been made to each page. Least replaced something used. Replaces pages with small.
Frequently?
Least frequently used. That's what it sounds like. Most frequently used. Okay. Yes. So now we have frequently used. Now you're going to have a counter with it. And when you go to evict, you either evict the one that was least frequently used or the one that's mostly frequently used. Least frequently used is hopefully specifying that, hey, this isn't used very often. Maybe we'll go with that. Most frequently used says, all right, chances are the one with the smallest counter was probably just brought in and hasn't been used yet, so let's use most frequently used. These aren't used that often because they don't they're just not good strategies in practice. But they can be.
Mid-frequently used.
Mid-frequently used.
Don't take the most or the least.
We'll just
Good
go
reasons
right
to
in the
keep
middle.
both of them.
Why don't you go right in the middle? Maybe that's the best one. I don't know. Okay. Before we go on to frame allocation, we need to talk about something called global versus local. Actually, let's pause.